Hello again. Now for this video, we're going to take a step back from the problem we were actually solving, and we'll take a look at what a Jacobian is and two different ways that we can calculate a Jacobian in Python. So first of all, what is a Jacobian? So say we have a given function where f equals, say, and I'm going to do this in matrix form, and f equals r cosine of theta, r sine of theta, and m times z. This is also kind of the format of our actual equations that we were given, x, y, and z for our curve. Now, the Jacobian of this function would simply be a matrix that on the first column has the partial derivative of the first row in terms of r, the partial derivative of the second row in terms of r, and the partial derivative of the third row in terms of r again. The second column, it's going to be pretty much the same thing, except it's the partial derivative of the first column in terms of theta, the partial derivative of the second row in terms of theta, and the partial derivative of the third term in terms of theta. Finally, for the last column, it's going to be the partial derivative of the first row in terms of m, second row in terms of m, and third row in terms of m. Actually, this value is supposed to be a theta, not a z. Okay, so there you go. So that's pretty much what a Jacobian is. And since our actual curve function only has one independent variable, which is theta or t, for our curve, these two columns wouldn't exist. We simply would have a 3x1 matrix that has the derivatives, the partial derivatives in terms of t. So now let's take a look at how we would do in Python. So first of all, let's just create an arbitrary function that we will calculate the Jacobian for. So let's define a function that as just a normal function that's like 3 times np cosine of 2 times x plus 3 times np dot sine of x. Now, just to make things a little more complex, let's just turn the x's into arrays where the x for cosine and sine are different. So I'll just make this the first value and the second value out of an array. So this function would take x as its input. We've got the function. So let's create a function that would actually calculate the Jacobian. So let's define that function as JAC. This would take our actual function, let's call it JAC, and this would take our actual function as an input. And just to make it a closure, let's define another function within this function. Let's call it Jacobian. And this would take some inputs, and this would return us a result. And the main function would return us the Jacobian. Oh, that's the Jacobian. Okay, so let's think about this. What do we want as the being returned? We would probably want an array of these 3 different values that would show up. So we would probably want our result to be an actual array. So let's call it np.array of result. Got that. Now, we established that Jacobian is pretty much just a bunch of partial derivatives. So how are derivatives actually done mathematically? So what we need to do is, so we basically, if we have a function of x, the derivative of the function in terms of x would simply be a function of x plus dx dx being a small increment in x, subtracted from the function of x, divided by dx, which is again a small increment in x. So we basically want to write this down in terms of Python, so let's do that. So basically our result would be the function of x plus h, let's call it dx, minus our function of x divided by dx. Again, we want the result to actually be an array, so we would basically want to calculate a bunch of results and make an array out of it. So instead of making this variable return a single value, we would want this to be an array. So let's just make it dot append. So we've got that. So since we're making this a list, we would probably want to start our result as an actual empty list so we can slowly add more values to it. So we have that. And we're doing this step by step, so this is probably going to be a for loop. So let's call it for I in range x dot size of that. Basically what this x dot size means is that it's going to take x as an input, and it'll see how many elements there are in the x matrix, and that would basically be the number of independent variables in our function. So what we would also want to do here is, Python doesn't work in a way that it simply adds two numbers together to create a function, does it? So what we're going to do is we would turn this into another variable. So let's call it xp. And xp would basically be x plus dx. Now we can simply perform this function on a list, so what we'd actually have to do is add these numbers individually by the list, the components within the list. So the item number I in xp and item number I in x. And once we've done that, we would also need to reset the value of xp. So that would mean xp would turn into x of I. The last thing we've got left to do is actually establish xp. So we would do that outside the for loop, and xp would simply be a copy of our x function. So that's all we have to do in order to calculate a Jacobian. So let's save this function into a variable. Let's call it JAC, and this takes our function as an input. We've got that. Now, if we want to calculate the Jacobian at certain points, let's say JAC and we would supply our the one thing I forgot to do here is that we need to supply an input to this function as well, this function within the function, and this would take x and dx as inputs. So we've got that. Now, there we go. Okay, so let's try and see how we would calculate a Jacobian. So for our x value, we have two different values of x, so that would be an array. So we would call that np.array. I want to send them values of np.pi over 6. So the first value of x0 would be pi over 6, and the second value of x, or x1, that would be np.pi over 3. And finally, we also need to supply a value of dx. So dx is basically a very small increment in x, so it just has to be a really small number. For now, let's just call it 1e to the negative 8. And okay, looks like there's an error here. So so since we're passing an array, this actually has to be enclosed by square brackets. That should work. All right, so we have these two values as the Jacobian. Now, another way to do this is just simply use the JAX module that we imported at the beginning of this video series. So the way to do that would simply be Jax dot Jacobian. This is a function within the Jax module, and just apply a function f to this function, and then we would also have to put argnums equals 0. Basically what this does is it tells the Jacobian the independent variable that we need to base this Jacobian upon. So let's store that in a variable as well. Let's call it Jax again. Got that. So if we want to take a look at the actual numbers, what it's going to be is, what we need to do is supply our actual inputs, which is going to be just this. We won't have to supply the dx now because Python calculates that automatically. And okay, it looks like there's an error here. Okay, it looks like the error we've made is that we used numpy instead of Jax numpy when we're creating our main function. So the only change we need to make is turn this np into jnp, and that should fix all of our problems. So let's see, everything works. Alright, there we go. And as we can see, these two numbers are very close to each other. So basically, both of these ways are equally valid ways of calculating the Jacobian. Just for sake of ease, we're going to be using this method to calculate the Jacobian of our actual curve.